manipulate how existing programs even behave. So we start by just creating a new project. Create a new project. For simplicity, we just go for a console application. We call it, how do we call it? Let's call it hook test. So function hooking is the process of overtaking the execution of a function. So what you want to do is you have a function that does something, and you want, when a program calls this function, to change it such that your code, your hooking code, will be invoked instead of this function. And in simple cases, this is all you want. You just want to do something only instead and completely ignore the original function. Or in not so trivial cases, you would want to do something, for example, modify the input parameters, validate them, change them in some way, and then invoke the original function, get the result from the original function, then perhaps do something more with the result, and then return to the original code as if nothing has happened. So in the terms that the program works, executes, and it just sees that it gets a strange result which normally it wouldn't get, or if normally you wouldn't want to return something that would make the program not recognized. But for example, one example would be if you want to make to make a program think that it is running in a terminal session. So that's one of the examples. Then you could hook one of the functions that is often used to check for that, and then return either yes or no depending on what you want the program to think. What you could also do is, for example, if you have a program that is throwing from time to time some error message box which you just want to get rid of, and automatize the pressing on the OK button, you could do that as well, just by discarding the message box if it has the error text you don't want it to, and other things like that. So when you write really your own code and expect such behavior, then of course the simplest thing to do is to call some wrapper function of your own, which then calls the library function provided by some library which you want to manipulate. But for example, if you would be already using some more complex library that is provided to you by some hardware vendor as is, and it has some incompatibility, is not working in a way you want it to, worst scenario, they give you a library which pops up a window that asks for something, and then you need to enter it, but you would want it to be a fully console controlled application. So there are many scenarios where you might want to alter the behavior of code which you cannot directly edit yourself. And using function hooks on functions which are part of the Windows API is one of the more reliable methods to do that. So in the first example, what we will do is we just include Windows H and throw a message box. So we don't need to provide anything here. Give it some tag. Let's see. So we need to give it some text. Test 1, 2, 3. You can give it some caption. My app. And MB. Okay, so we just want one message box. So this just does not too much. It just shows you a message box. And then we will look how we could change this such that we can intercept this call. Okay. So first thing we want to do is we want to get the address of the message box function we want to overtake. So let's make a pointer. Message box v, and write to it the value of. So message box is a preprocessor macro which, depending whether you are compiling Unicode or ASCII, will either invoke the v or the a function. A is for ASCII, v is for white, i.e. Unicode characters, and pretty much all the modern projects on Windows will by default be compiled to Unicode. So we just stick with trying to hook this function. What else do we need? Then we want our detour function, so we define an own function which has the same prototype as the message box v function, which we can just copy from here. Zack. We of course need to change the name, like my message box v. And let's say for starters we want it just to return with nothing. So return, what was it? ID OK. Oops. So if we do this and then hook it this way, we'll just make all the message boxes always quit with the OK button was pressed, even if the message box doesn't have an OK button, like the retry, abort, cancel message box. So that will need some improvement, but let's start with that. So then we want the address of this. Underscore my message box here is then just this thingy. Oops, that was a copy and paste mistake. Okay. Okay. So the way we will want to redirect execution to our function will be by writing a jump instruction at the beginning of the original function, such that instead of doing the original function prolog, our hook will just make a jump to the address of our own message box. So in order to be able to do this, so first we could just try to do it in the most straightforward way we can think of. So we just create a helper structure, which is quite useful for those things. Onion then we need word and int64 quad word q, and we call this code. Okay. Yeah, so what do we start? We have code. So here we can assign p byte to the beginning of our helper, the address of our message box. Where do we have it here? Charge 10 is the message box. Okay. And now what we can do is we can use this code object to write those different sizes of data types. So for example, if you want to write a byte, we make byte plus plus something no x12, and the nice thing is that it increments the address which is stored in this object by the size of the element. So instead of, if you would not use such a smart helper structure, would be just using charge 10 let's call it data is equals. So if we would want, then we would need to make like something like this. So the thing we would need to cast. Okay, uchar is a stupid, it's a boring example. Let's go with q. Let's go with d, because d is reasonably 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we would need to cast it to word asterisk is equals whatever we want, and then in the next line we would need to make plus equals of the word. And so this way you see we are saving pretty much 50% of the amount of things that we would need to type if we are using such a helper structure. That is a pretty nifty trick. But going back to our detour, so we now will need some way to assemble code, assemble individual assembler instructions, and see their binary representation. So modern x64 compiler doesn't allow you to inline assembler, but what you can do is you can use one of the very many online available assemblers. They are quite nice. You just write some assembler code, select the bitness, click assemble, and it assembles it for you. So what we will want to do here on the assembler side will be, we first want to move the address of our detour function into a register. So move absolute rax, comma this thing. I then we will want to jump to our we want to have a jump jmp to Rex, and that's pretty much it. So we only would want to write two instructions, only override two instructions, but we need to find out how they would look binary in binary representation. That's not great. I will make this smaller so that we can switch here. So we write move ups, comma x, comma. Then we want to have something that we can recognize. So let's say null x 1 2 3 4 5 6 7 8 f. We will later replace this with something else, and then jump rax. So jmp. Then we just press on assemble, and the thing returns us the machine code that represents this particular instruction that we just typed. Oops. So now we know what we want to write. So we see that this part corresponds to this part, and the whole move rax seem to only be those two bytes. So first we want to write a word, and those two bytes, since it's in reverse order, would be B8 4 8. Okay, and then we would want to write our address, so we use the Q, and then we just write our the address of our my message box. And now we want to write our jump instruction, which is again just two just 2 bytes. And again, since we need to cast it Q64. So here again, this would be A0 FF. So now when we run this, it should just not show any message box, just return. So we can return out from our function. So if we run it, I forgot something. It crashed here because the memory area we are trying to write is of course not writable by default, for good reason, security. So what we need to do first is to make this area writable. So we can use the virtual protect function for that. We need a helper variable that will hold the old page configuration flags. Virtual. Then we need to specify the address which we want to unprotect, which will be this thingy. Then we specify the size, so which count of bytes we want to change the protection for. Let's here go with something short like 32 bytes. We don't need more. Then we want to specify the new protection configuration, so we go with page execute read write, so that you can write to memory which is executable, which is usually a not safe thing to do. This is why also here by default the last parameter will return you a copy of the old configuration. So once we are done with our mangling with the code, we can just call the same function again, and then we just provide our alt protect as an input. Then it will basically restore the whole page permissions, and then this parameter is there just because it's necessary. We don't care for its value. So now when we run it, that should no longer crash, but instead it just skips over the message box. So we can now make a breakpoint here to actually watch the code step by step. Debug Windows disassembly. Where was that? That's here. Okay, let's put it somewhere on the side. So it fills up the parameters, and then it calls the address. But as you see, here we have our own instructions instead of the original ones. We load the address, we jump to the address. Then we have here a jump table which is created by the compiler for our own function. Then when we go in this, we end up here in this function. which does a few things which we really don't need. So we could actually change the configuration of the project to disable all this mycodes thingy. And where was that general code? It was called support mycode somehow. Code generation maybe. Okay, let's go to all options. That has a search. My support just my code debugging. We don't want that. No. And we also don't want all this unnecessary jump tables. That was somewhere here. Where was that general? No, that will be somewhere with maybe here. No. Enable incremental linking. We don't want that. Okay, let's see. That should clean up the assembly generated by the compiler a bit. So we have here the same code, and we have the jump to Rex, and then we jump directly here. So it eliminated the unnecessary jump table and also reduced the amount of code in our hook function. And then of course it just makes the return, and then it just returns here. So what we now could do is, so what we would want to do next, for example, would be we would want to check the parameters. So let's say, well, this says test 1, 2, 3. So we would want to if str. This just searches one string in another string. What was it? Let's say we want to suppress everything that starts with test. L test. And if this is not null, then we just suppress it. But now, if it's not null, what we would want to do would be to invoke the original sandbox function. The problem is, of course, that we have overwritten the original sandbox function and cannot longer really call it properly. So one strategy would be to make a backup and then restore the function for the invocation. But then, of course, this removes our hook. So depending on what you want to do, this might not be what you want ultimately, because you probably want your hook to work in a multi-threaded scenario in which you should install the hooks as early as possible, block all other threads from execution, and then just don't remove your hooks at all. If you want to disable them, we would just have a flag that would then just directly redirect to the original function. So what we now need to do is to create a so-called trampoline, which will be a piece of code which contains the initial portion of the original function plus a jump to an address after the code which we have modified. So let's do that. Though before we do that, let's maybe disable our hook and first see how the original function looks. So we can hash if null, hash and if. We'll just run this and then we'll write down the original function prolog. So let's just take a couple instructions from the beginning. This should probably be sufficiently many. We can switch this here to show bytes, then we know how many. Yeah, this will be definitely many enough if we take those. We should copy the bytes just to be on the safe side. Of course, if you want to more practically hook something, you would just use a library which is implemented such that it creates a trampoline for you automatically. It's not customary to make hooks and write the trampoline by hand, because since we are pretty much messing around with a Windows built-in function, you can expect at some point in a newer Windows release this function to change in some way, and then your hook would of course no longer work, your trampoline would be wrong. So what you would want normally is to dynamically generate a trampoline, but this is quite sophisticated since you need to analyze the code that is there algorithmically and then generate the whole trampoline. So this is too much for one single lecture. Hence we will just do this by hand on one single example instead. So let's dump the code we have copied. Here we don't need the addresses. Sorry, someone's calling. One moment, please. Okay, where were we? Yes, so we dumped the code. Then what we would want to do is to find some memory which is as close as possible to the original function. So let's make a loop for that. We'll just start at the address of the function which we are hooking. We don't put anything here, and then we increment by the size of one page, 1x1. So that's about 4 kilobyte. Oh, actually, it's quite exactly 4 kilobyte. And we will need a variable to hold that. So let's go for the start with void tramp short for trampoline. We initialize this with null just to be on the safe side, and this is then equals virtual alloc, and then we specify where we would want the allocation to be. Oops, that didn't. And then we specify the size. Let's say with 32 bytes should be enough. Then we specify the allocation type, mem commit and mem reserved. Yes, and then we specify the page protection, and here we go with our execute read write. Actually, we should probably do this at the very top. Yeah. Okay. Strich punkt, and if this is not null, we can break. Actually, we could put this into the loop condition. Since we have pre-initialized it with null, it will be null, and the loop will repeat well pretty much endlessly until it finds an address where it can allocate the memory. In the production build, one would probably try to add here some counter, like if the thing tried like a gigabyte of addresses in the address space, then give up if nothing was available, because sometimes there might be very odd edge cases and you would want your code to then just terminate with some error message that hook could not be installed, and that's it, instead of showing instead of just running in an endless loop and wrapping around and repeating the whole thing. Okay, so let's think. So what else will we need? So we have so we will need, of course, a way to call our trampoline. So here, before our function, we'll define a function pointer. We had already today function pointers, so here we will do them in a little bit more detail. We can so one thing, of course, is you can always write the whole function prototype whenever you are using the function pointer, but if you want to save on typing and expect to use it more than once, you can use typedef to define message box to define your own type, which will then be used. So we can just define it like this. That looks better if we do it like this, and then we can define a variable of this type. And that's gonna comment I just message box. Okay. Initialize it with 0. And okay, and here, without having yet done the trampoline, we can already use it. here we just pass the same arguments we got from the top. Although we can do some shenanigans, we can change the message box title to always say hacked app instead of my app. Then we specify the type. And now if we of course call it, it will just crash with a null pointer dereferentiation, since we have not yet created or assigned our trampoline. And also the compiler is complaining because that might be null, so if this is not null, just to be on the safe side. Although I think the Windows API would just crash if you would give it a text of null. Although I haven't tested that recently. Okay, so coming back to our trampoline, so we have our trampoline here. So the simplest thing what we would think about building the trampoline would be just to copy whatever we have here up to the size that we need. So let's say we can leave it here, we can do this, and we actually know the length, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 12 bytes. 12 bytes would be 2, 3, 4, 5, 6, 7, 8, 9, 10. So we would need up to here. That will give us more than 12 bytes of room, which is good. So for the trampoline we can use the same method here. Or actually we could also do it slightly differently. We can take this variable. We just use this directly here. Okay, we don't need to define it, obviously. It's already initialized with 0. And we just need to cast to p underscore HP. So we have the right type class. Here we are typing, casting the thing. Okay, we should maybe add some comments. So here first would be and here we will have okay, so what do we have? So first thing is a word, pay word, sorry, a double word, plus plus is equals null x. We need to remember to write those things in reverse order, since we are using little endian notation for 8. If you would write this, of course, in like one byte at a time, then you would of course write it in the right order, but then you would need more lines, and that would be not so good. Why is it complaining? The asterisk is missing. Okay, then 3. We're writing 3 bytes is annoying. We will just write a word, sorry, a word and then a single byte. So we write a word. 2 first bytes, 33, 5. Or actually, we can write the whole thing as 3 bytes. That will maybe look better for us. So null x4 5, null x3 3, null xdb, yes. And then we have 1, 2, 3, 4, 5, 6, 7. So this is a relative instruction. How do we handle that the best thing? We can throw this into our disassembler. That shows us the actual numbers which the thing used. So we have 5280. So this portion is the offset, and this portion here is the actual instruction. So can write this down here, for example. So we want only the first 3. So let's do that again. Like this. So we have 4 4, 9 and 1D, 1D, and then we have a word, number word, which is this. Okay, and that should have given us enough room. So what we now want to do is we want to add a jump to the original function. So we already learned how to do that. We take our jump code, and here we just specify well, the target, the address where we want to jump. So we first need to compute the address where we want to jump to. Let's call it underscore underscore trampoline target, and this we will need to compute. So this thing is our OIN64 jump target, OIN64 of our original function. Where was that? Here. And then we just add the amount of bytes we want it to jump, and we need to jump just after this. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we just need it to jump by 14. So we will end up in this jump instruction here. This is our trampoline target. Okay, and then we have our starting code. So we can write here, just so that we know what it is. Move x, comma, jump target, jmp x. Okay. Good. And one warning ahead. The way we did it now will should create a crash. So let's try that. Wait, code D, message box. It should not crash here. Did this allocate the memory successfully? No, it did not. While? Sorry, the check is wrong. It should repeat as long as it is null. Okay. There was another mistake, an intentional one, which we have that should trigger now. Well, it did. Sorry, it didn't trigger because we did not try to invoke the trampoline. We need to change this to test to another test. So like test 4, 5, 6. We check for 1, 2, 3, right? No, we check for test. Then let's check for 1, 2, 3. That's easier. 1, 2, 3. So let's make this into a check 5, 4, 5, 6. So now again, the first one will work because we are not invoking the trampoline, and the second one, where we will try to invoke the trampoline, should cause a crash. And it did. Any ideas why? Okay. So if there are no ideas, then I'll tell you. The bug is here because what we have as the code, so this one is fine. So something is fine. This one is also fine because it just operates on registers. It does not do anything else. So XOR, a register with itself is pretty much just make the registers 0, and they're using often XOR because this often gives you the shortest code. Sub is actually just a subtraction, so this is fine. We are just creating some new stack space. But what did that start? Wait, sorry, I copied it wrongly. This one is here, and that one is there. Yeah, but this instruction here, the longer one, that one. Let's go with this part of the code. What it does is it takes the instruction pointer, so the actual position where the CPU is executing right now, and adds an offset to it. So when we copy this code to another position, the instruction pointer will have a different value. If it still adds the same value to this position, the resulting number will be wrong, will not be what it should be. And then the whole thing starts to fall apart. So what we need to do is we need to adjust this offset such that it will be what it's expected to be. So what we will do now is we will calculate a displacement value. So the trampoline displacement is equals which are our trampoline address minus which are our original function address. So now since we allocate, well, at the address will always fail, but like the next page or a few pages further down an address, we know that this one will always be bigger. So we can just make a minus. We could also try to find some pages to allocate the memory before or after. Then we would need to make the displacement positive or negative. But since we want this to be a simple test case, we just go and do it this way. So when we have our displacement, ideally we should just need to, I think, subtract the displacement from the value. And now the resulting new value for the operation should be correct. Let's try it out. First, let's maybe make this look nicer. Okay, so let's run. Okay, so I said the first one does not do anything, and the second one shows us successfully a message box, and as you can see, the header was changed to hacked app. And then when you press OK, it just continues normally. So this is a simple example of how to hook a function. As said, this is because of the manual creation of the trampoline a rather unpractical example. So in real life you would just use a library which does this for you, or write your own library which does that, but this is rather sophisticated, so we won't try even to write such a library ourselves. So are there any questions on this? No questions? Okay, so if there are no questions, then the next thing would be to see how this can be used in a more useful way. So currently we are limited, the way this was demonstrated here, to use this in your own program, and you can only manipulate system functions which are used by your own program. So as I said at the beginning, in this particular scenario, you could just write a wrapper for message box and have the same result, and then you would just need to use the wrapper instead of the original message box. So what we will do next, we will write an application which just calls message box, and then we will try to start this application and inject the hook into it. So assuming we have an application which code we cannot alter, this will demonstrate us how we can, without changing the application on disk, still make it behave the way we want. Does that sound more interesting? Well, good. So let's create a new project. Create new project. We'll just go. Wait, why new project? We can actually add projects to this project, so that's better. Add a new project. Console application again. We will call it target app. Oops, I have a typo. Damn it. Wait, let's correct it. And remove. Again, add new project, application. Okay, now we are typo free, and so this application will just throw either we just make it throw two message boxes. Let's do it a bit more sophisticated. So we include the age, and then we make if message box null comma l question mark comma title l comma mben yes no and mben icon question, and if this is yes, either yes, then and f failed and oops and return -1. We need stdio message box null comma l this program does work or does not work. Well, if it doesn't fail, then it works. Does work. Ausrufezeichen, comma title again and mb. Okay, or mb information. Should be info. Econ information. Econ information. Okay, and f. Okay, and return null. Title needs to be white characters. Okay, so this app is quite easy. It doesn't do much. We don't even need to test it. It will be working. And now there would be two strategies how we could manipulate it. We could create the application, and then before it's actually started, try to write around in its memory address space. So that would be one way. The other way, which is quite common, is that we start we create the process suspended as well, but then we just modify its memory in as far as that it would load a DLL which we can specify, and then within the DLL we can have then our hooking code. So usually the second approach is much more useful, since it's much more powerful. It gives us the ability to act already within the context of the application before the application is actually running, at least on a superficial level. So as soon as any code gets executed within the process, some parts of the ntdll will be executed first, and without a special hook, it is difficult to mess with this part of the initialization. But the simple del injection will already guarantee that our code will be executed before the main function of the program will be started, which is for most cases good enough. So let's create a few more projects. One will be just the injector, so let's call this DLL. How do we call it? DLL injector. DLL. Create, and then create a DLL that will be injected. Add project DLL dynamically loaded library. Injection there, or inject DLL. Could also call it hacker DLL. Let's go with hacker DLL. that sounds sinister enough for our purposes. Okay, so in the DLL injector, we don't need too many things. So there are again a couple strategies how such a DLL injection would be done. The simplest one is just with using the create remote thread function. So let's start. So first of all, we want to know where we are right now. So team. So now when we compile the project, all the files will end up in the same directory. So what we want to do now is just to find out the directory we are in, such that we can work from that. So let's call it LDR path. So it's our loader path. We go with max path. Max path is 255 characters, and this is often used restrictions to how long a path under Windows can be, but technically these restrictions only apply if you are using the ASCII version of the Windows API. If you are using the wide character versions, the real file size limit that the API can handle is 65,000 characters. But since many applications don't use, or rather are still using the max path restriction, it is good to try to limit your paths to this length, while of course it would be good to add support for longer paths, but since we just want a quick and dirty DLL injector, we will not add more memory for that. So get module file name v. This will give us the whole path of the current, well, of actually any loaded library, but if we pass null instead of the module address, of the module base address, then we'll get actually the path of the main executable file which has been loaded. Then we give here the pointer where we want the data, and we tell it what's the longest string it can write in there. And then now what we want is we want to remove the something.exe. We just want to have the path and including the last backslash. So we use the white char string reverse character search function. We pass to it loader path. Of course, the code is here also extremely hacky, since we are not even checking whether the returned parameter is valid. We just add +1 and make this null. So I lost a bracket somewhere here. So obviously, if we would want to write a proper application, we would check whether this succeeded, then whether this returned not null, so whether it found the backslash, and then maybe some more plausibility checks, and then only we would do the string modification. But since we are writing a hacker application, we are doing it the dirty way and not checking anything. Exit path will be the path of our target. So we vcs cpe, copy our loader path to our exit path. Oops. Then we use vcs cut to append to our exit path target app.exe. Okay, so we have the path for this. Then we will prepare some structures which we need to start a process. Startup info v se. We initialize it with null. Then we need the process information pi, which we also initialize with null. Now we can create our process. Create process v. Application is our exit path. It could also be a whole command line. So then command line we don't use. So we pass null. Process attributes null. Thread attributes null. We don't specify anything. Inherit handles false. We don't need that. Creation flags, that's the one we need. Create suspended, so that the process is made but doesn't execute any code. Now environment null. This will just initialize the default environment. Current directory, if we say null, then it will also just take the directory we are in already. And now we specify our startup information and our process information structures. In a non-hacky program, we would check whether this succeeds, but since we are a hacker, we don't care. And well, actually at this point we already can start the program, so maybe we should test that. But let's not do anything. Let's just return null. So we need to compile this. Actually we can set up some dependencies. So we are in our which one do we want to run? We want to run the DLL injector. So if we are in the DLL injector, then we so that's the first thing. Then we set the dependencies of DLL injector. It depends on the target application, and it depends on the, or though now it's not yet, but we can set this dependency because it will depend on it later. And now when we just start it, it will automatically compile all the dependencies before it tries compiling the project. Oh, something crashed. Yes, it doesn't like those unsafe functions. Okay, let's use the safe versions then. So max words is path. You could also specify a preprocessor definition to allow the thing to handle to allow you to these unsafe functions, but at some point it's reasonable to just always use the safe functions, especially that they are not okay, we didn't see a message box, so something didn't work out quite right. Let's see what. So let's set. Oh, Screamedy, we made a mistake. We forget, since we created it suspended, we did not resume it. So it's actually created it just sitting here, not doing anything. We can resume it by hand. And now it crashed, which I'm not sure why. But for our test, we should add the resume thread function to our pi.thread. So this will at least ensure that the functions that the it starts, and now it actually works. Do you want the program to fail? No, this program works, so it works as it should. But of course, before resuming, we will want to do our code injectee thingy. So first of all, let's create another path which will contain. Let's do it over here. Oops. Remove the white space, which will contain our DLL. So that will be called. We should have used the opportunity to call it Hacker DLL. Let's do that. We did it actually. Oh, perfect. DLL. Okay. So we have this. Now what we will do, we will allocate some memory in the new program. So void asterisk address via 12x the process. We need the X version such that we can specify the process handle where we want to allocate it. So as address you just give null because we don't care where it allocates it. Size, let's allocate just the whole array. Comma. Do we need something like mem commit and page. We'll need page read write. Rage. Page, not rage. Page read write. Okay. Now we need to write our path to this memory. So write process memory again. H process. Now we need the address. Comma DLL path. Comma size of DLL path. Okay, that wants to be cast to void asterisk, I guess. Oh, copy and paste bug. That should be called DLL path. And now it would tell us how many bytes it wrote, which we don't care. So we just give null. And now we need the address of the load library function. So void asterisk. So this function just takes one argument, which is a path to a DLL to be loaded in the process in which it is executed. It will return the handle to this DLL, so the base address of it, but we don't need that at the moment. And now we'll be creating our thread. So handle the remote thread. So pi process, comma, no security, stack size default, and then we need this lp threads, lp start routine, and we cast our address variable to this thingy. Parameters is then our address here, zack, comma, creation flags null, and this is not relevant. Oops, that is not null, 0 null, zack. Then we want to wait for this to finish, so single object, and we want to wait forever. So the thread will be started. The thread will execute the load library function, which will load our DLL. And once it finished, then we can resume the actual process, which will then actually just then start the main function of the original process. Let me quickly check. This is missing. So let's quickly close Visual Studio and install a helpful tool. There is a nice extension for Visual Studio that allows you to debug child processes automatically. So in our particular case, we could just wait in the debugger and before we make the resume attach to the new function, but since we are lazy, when they put it Visual Studio, which version did we have? 2002, so then sorry, 2022. So let's get the what I put that tools. Yes, I put it here. If you Google for child process debugger, then you will find it in the Microsoft extension store, and it's free to download, like all the, or at least most of the other extensions. So that needs a second to install. It's slow. It's terribly slow. Okay, now it's done. Zack, zack, zack. Okay, we open our hook test. Okay, then we go to debug. What was it on the child debugging process settings? Click on yes, save. Okay, maybe before we start, we should add some comments. So, then here, zack. The line break somewhere. Okay. And we're done. Okay, so Now we won't see much, but we can go to the DLL and put a breakpoint here, so that we will see that will actually be injected, if everything works as expected. Is it working, or is it... it didn't work. Why? Let's see. So, zack, zack, zack. So here we create the thread. At this point the thing should be resumed. But it was not. Create a thread which should be running. Okay. It's waiting here, but this is still suspended. Okay, maybe this try debug thing is interfering. Let's quickly disable this and try by hand, but normally that works just fine for me. So we start, and before we do it, so debugger attach to process target app. So we are now attached to the new process, and now we create the thread. Yes, and code gets executed. Yeah, why not? Load. And then we resume again, and we end up here. So okay, this child debug thingy somehow was not working as it should. Manually it works. So here we are now within our... We can actually check it from here. In our target app, when we list the threads, which one should be this one? We are in our load function at the beginning here in our DLL. You see that there are actually quite a few other threads. So we have this thread, which is the main thread, which will execute the main function, and these three threads here are created by Windows by this initialization code from NTDLL, and they are used to load statically linked DLLs into the process. So we could change this such that it will not create a worker pool and only uses one thread, which sometimes is actually useful. But for this very simple case we used right now, we just leave with it. We don't care. If we now make, of course, play, then here we have the wait, which... Okay, this will be called a few times because it is called once when the DLL is loaded in the process, then it's called each time when a thread is created for every thread, then whenever a thread is terminated, and then it is called again when before that application terminates. So this function is called quite often, so we remove the breakpoint now, and then when we resume the main thread, we will see that we still get our normal behavior since our DLL is not yet doing anything. So we stick with this breakpoint, but remove the other two. And now we will copy pretty much just the content of our hook test to our DLL. Yeah, we can... I think main is already... sorry, I think Windows H is included in this PCH. PCH, H... Okay, just framework, and framework includes Windows H, yes. So we don't need the... This is the header, but we need all the rest. Zack. So we don't need this and that. We are here in our DLL main. And then we need only our hooking code. Zack. So here we go to the process attach case. Get the break, and then actually we could maybe keep our thing in their own function. So void so we put our hooking code here. This one we don't need, and this then we call from our DL main function. And now when we run the thing, it should well, we would want to change what we're doing in here to be more in line with our goal. So let's say, what did we want? We did say we want it to bypass. So we want the message box. Which one was it? The first message box to not be shown. We don't want to have to tell the program that we don't want it to crash. So we can copy the text, which we know to expect. The asterisk error. Why is it complaining? Const. Okay, if for CSCMP string 1 is this with our text. So if this is null, then we just return ID. Wait, what was the question? Do you want the program to fail? The answer is no. So we want it to be ID no. And in all other cases, we just take the title and let the application execute as it should. Yes. Nice enough. Let's run it. Okay, something's wrong. That thing was blocking our debug data. Still blocking? Okay, then let's just close it. Okay, so we want to attach. Actually, we don't need to attach the debugger. We just can check whether it works. This program works, and it said hacked app in the title. So now, again, with the debugger attached, we can target app, put a breakpoint here, a breakpoint there, and here a breakpoint here, and run the code. We forgot to attach the debugger. Again, run debugger, attach. Where is that? Attach to process, target. Zack. Now if we run play, okay, it always brings us to a particular location in the NTDLL when it finds that a debugger is already attached during this early initialization stage. So we just ignore it, just press continue. And then here we are in our injected DLL, we install the hook, and then when we try this function, then we should be able to step into it. Then we end up in our detour. Zack. Compare, we return our no, then we go out of it, then we end up again in our detour. Then this time the text is a different one, so we show our we invoked the normal trampoline, and it works as it should. And then of course we can continue from there. So we click print OK and terminate the application. So it's working nicely. And pretty much the main reason why we would not want to do the whole hooking the whole hooking business entirely from a different thread, but are using a DLL for it, is that if we would do the whole hooking from somewhere else, we would need to provide our detour function written in assembler or somehow compiled to a position independent code and also injected into the other process. And since this is rather a cumbersome thing to do, it is for us just much more convenient to, like this, inject a whole DLL. In principle, yeah, the DLL needs to stay loaded, of course, in the process for as long as the hook is installed. So ideally, we would want to have here something to uninstall the hook. We can do that, but one thing we probably should try to do before is to get rid of these additional threads, which are there created by the loader, since they might cause troubles in more sophisticated injection scenarios. So we will do that next, unless there are any questions right now. So are there any questions? No questions? Okay. So let's go back to our DLL injector. Okay, so what we will need is we will need to find out the so-called process environment block address of the new within the new process. So we can do that by first determining the thread environment block of one of the threads within the process. So we can go with this what was it, with this thread. So what we have created it before, we can do it here. So here let's say and here we will say so we will be using this. We will need some more things here. Internal HUD, it should have the right headers. Anti oops, query anti information process PI process, comma we can actually, I don't need that, it's good. Process what do we need? Let me think for a second. We need the process information, process basic information, process information, comma reference, comma season of comma null zack. Okay, so this contains the PEB address, that's the process environment block, and with the PEB address we can then start to mess with it. So let's see. So we can check the definition of the PEB. It should be, I think, defined here. So we see here the whole PEB, and what we need is the process parameter. So this thingy. So we need this offset. So we can do. So what we are interested is PEB punct process parameters. So we go with just read the prods, or just parameters, wurscht, is equals field offset of PEB, comma this thing. Then we have the address of that, but this is just the offset, so we need our basic information. Let's start with PEB equals let me think. That will be this. Sorry. Plus PEB offset. So this is just the address of the PEB, and this is, let's here a change. So we have the address, and then no, this is the address where the address to the PEB is stored in the process environment block. So now we need NT, or just read. You can use any. So there are, for many of the functions you have just a function like what was it, read process memory? Yeah, the normal versions are you have the NT read. No, read return. What was NT? Should be defined. It's not defined. There are quite a few functions in the NTDLL which are not defined in the standard headers. So we just stick to the and these functions are usually then called by a wrapper function located in the kernel 32 or kernel base DLL. So if we would step through this read process memory, at some point it would bring us to the anti-read virtual memory function, but since we want this to rather implement it quickly, we just go with these functions. PI process, comma, base address is this, comma, then where to read to. So let's make a int64 let's go with the annotation prods param and large p. Let's go with that. We can initialize it to null, but we don't care. We want to read into this with the CZ of that, and we don't care for the result. Peb address. What is this thing you want to avoid? LP void. Okay, then we need to cast that. Oops, one. Okay. So now we will have the address of the process parameter thingy. We can go back to our peb definition. User process parameters. So that's the structure we want. Yeah. Okay, and now so we have this, and then we want within this thing to find the next offset. So we want this thing. What was it called? Loader threads. Loader threads. So we go with int64 large, very large. Loader threads offset equals field offset comma loader threads. Why is it complaining? Our definition is highly incomplete. Then let's find a better one. So the process hacker repository on GitHub, okay, that's not on GitHub, that's on SourceForge, we want the GitHub one, contains a library called PHNT. Here, that's the path, and there you can find a huge amount of headers for Windows which contain all the undocumented parameters which you ever might want to use. So you see the difference between like what Microsoft includes in their headers, a lot of reserved and then two thingies, and here you have pretty much everything reverse engineered and explained. So let's copy this. On the first glance, we might need a few more definitions from the top, but let's see if this one is enough. Of course, the problem is that this definition is already exists, so we need to rename it like my RT something 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 my art. Okay, without this underscore. My RTL, yes, that is good. But as you saw before, it was complaining. This will not compile because we actually need this structure and that structure as well. Although one of them might be an enum. So let's quickly check and find the definition for the. Okay, this one is fine. So there is nothing too complicated about this one. It does not include other structures. It is just a Unicode string which the definition is provided, and it's a handle. And the other one, RTL drive letter current dir is also nice enough. Does not seem to contain anything oops, I didn't copy. Particular problematic. And since they are not defined in the headers we don't need to rename them. So okay, we need this definition as well. Wait, oops, what was that? Which is just 32. So this is the last thing, and now our structure should give us the right offsets. So we have here the offset, not quite, it's just the offset with regard to the prods param address. So the loader offset thread address will be the process param address plus the offset. So now we have the address of the loader threads variable, and now having this address we can manipulate it. So write process memory pi h process comma base address will be this. I just need to make it a void asterisk. We need something to write to, so long that was, and we want this to be 1. Oops. I think if it's a misstep. I think if it's 0, then it will just take a value from the registry during the later initialization stage. So we don't need to read it. We will just write that. Comma L. Okay. So now if we run and attach to the thread and get into this breakpoint, we should see in our task X, it was lying somewhere on C, I think. I didn't install that. Yeah. No, we don't need that admin. So when we look into the threads using Task Explorer, then we will see that we should only have 2 threads visible. That thread we created for the injection and the main thread which is still in a suspended state. So let's run that. Oh, something failed. Unresolved external symbol. Yes, that was to be expected. This needs a new library include. The ntdll.lib. Zack. Okay, debug, attach to process, target attach, and run, and now when we look inside, we only have 2 threads. There's still suspended RTL user thread start, which will then start our main, and our injected thread which just calls load library as the load library x here as the main function, and then internally calls the TDLL loader load DLL, which then loads the DLL and at some point invokes the DLL main function with the process attach flag set. So if we now start, this should just start as normal. The program works. Good. Any questions at this point? Do you find such things interesting? Do you want to see more of this? Okay, so what's next to show? We could look into some other thread injection methods. So if we don't want to use this load library. Now, one limitation at this point to think of is that the way we are doing things here assumes that the injector is of the same architecture as the process we are injecting our code into. So This is something that usually is the case, but in principle you can write a code injection mechanism such that you could inject across different architectural boundaries. This, however, is much more complicated. So the simple case is if you make an injector which is itself 64-bit and can inject into a 64-bit or a 32-bit process. Because there are some functions available which help you with that. The other way around, injecting code from a 32-bit process into a 64-bit process is very not so easy, so highly not trivial, because for once you are missing some of the functions that you would need to use to obtain the right offsets within the program, and secondly, because it's also not trivial to obtain even the address of the load library function. So here we can just where was that? Here we just write an equation like this, and this thing will have an address to the jump table entry in the NTDLL, in our NTDLL, which is the right address. But for a process which uses a different architecture, it is of course to be assumed that the load library address in the NTDLL version of the process of the architecture which the process is loading, it will of course be different. So if you want to obtain this address, you would need to, from a 32-bit process, you would need to execute a load library function in the 64-bit context, which can be done. So there are tricks how you can execute 64-bit functions from a 32-bit code. I can quickly look if I find an example of that. So how was that? Yeah, so there is a library for doing this. It's probably also on GitHub. Yes. Zack. Oops, I closed the window again. So this library, WoW64X, allows you to execute 64-bit code from within a 32-bit process. And the reason why this is even possible is that when a process starts on Windows, even if it always loads the native version of the NTDLL. So here we are in the CMDX, and if we now load the 32-bit version, Windows syswow32 and the X. So this is just the same command line interpreter, just in 32-bit. If we look with Task Explorer into this, so it also indicates that it's now a 32-bit process. Then go to the loaded modules. Then we see that pretty much everything loaded is within the 32-bit address boundary, but a couple DLLs here at the bottom, like a copy of the NTDLL, so the native one, and also the WoW64 DLL and WoW64 WinDLL have been loaded, and they are native 64-bit DLLs. So those programs running, those 32-bit programs running on the 64-bit Windows have a 32-bit copy of the NTDLL, which for most part is just like the normal NTDLL on the 32-bit Windows, except for all the system calls, and then it has also the 64-bit version loaded. And the way this works is that when you want to invoke a system call, it will execute a transition from 32-bit to 64-bit within this entity and call the code within the native NTDLL, and the non-native 32-bit NTDLL will take care of translating all the arguments from a 32-bit representation to a 64-bit representation, then do the syscall, then translate whatever return values have been returned back to a 32-bit representation, and then return it to your 32-bit application. And this transition to 64-bit code can be pretty much executed by any part of your code, so it's not anything magic. It is just a set gate on the in the CPU, which you can call with the right CPU instruction, and then you can call any function without having your parameters go through this 32-bit to 64-bit translation. So obviously, if you would want to call a function that would return you the address of the NTDLL, of the native NTDLL on some 64-bit process while you are yourself in a 32-bit process, then all the address variables would be truncated down to 32-bit, which would be useless for your application because you would want the actual full address. But if you invoke those functions on the NTDLL directly from your own code, then you don't go through this 32-bit to 64-bit translation layer, and the arguments that you pass around are just the native 64-bit arguments. Of course, this also means that all the data structures which you might be using, like here, where do we have it? Our PEP structure, this one, or the myRTL user param structure. Those structures, you cannot use offsets you obtain from them because they would be then in 32-bit while you would want the numbers in 64-bit. So you would obtain the right offsets manually somehow, and then you would write here the resulting. So you can just write this as const, and then the compiler should actually already tell you the value that it would assign. So this would be 32. So we would just do something, something like this, so that you don't never use the field offset. Just instead use the exact known offset that would work for your particular use case. And of course, if you have, if you are, for example, using a function like here, query process information. So this, I mean, this one is rather boring. But if you would want to run other of this anti-query information process or set information process functions, you would need to get the right 64-bit implementations of these information structures which you are passing to this native function. We could try using it, but I mean it's a rather large sample if you want to really go through it step by step. So I'm not sure if this is interesting. Well, it is interesting, but whether we can do that in the last 30 minutes. Another thing I could show you maybe would be other techniques to inject ADLL into something. Well, that would also take some time. I think the normal use case is that you just create your injector of the right bitness and then you are set. So let's not spend too much time with this. I will just add here a reference. So somewhere at the very beginning, a comment. Architecture bitness as the target process. Okay. So you might wonder when it would be interesting to make something that can inject code across different bitness boundaries. And for example, one use case for that would be if you would want to make something that injects some code into a process, and when this process would spawn another process, then the new process which is created would also get injected, and like the next one and the next one, so that you can inject a whole process tree of processes just by initially injecting some code into the first process. Depending, of course, on the scenario here, you might not need injection across bitness boundaries because in these scenarios your code would the child processes probably would be of the same bitness, but this is not guaranteed. So someone might have written a program that has a 64-bit process, or rather 32-bit launcher, then launches something 64-bit. So this actually is something we maybe want to try to do. So we could implement some. So we can change the target app such that it starts itself with an additional parameter, and then we would want to try to make this injection. Can we do it in a half an hour? Maybe. Let's try. So get command line v let's quickly check out. So let's first change our target app. So we set the target app for now as a start. I think I will just quickly check whether this contains the whole argument. Can we somehow get this quickly? Okay. So since we are lazy, we will just check if what's the s the r, comma l, comma 1. This is not the right way to check things. Check a command line parameter, but it's like the quickest and dirtiest one. Qt has a really nice function on the Q application that allows you to access every single command line argument by index, but we just check whether the command line contains it, or rather actually whether it not contains it, and in this case, and shall execute v create process. Let's do that one. Oops, information. Shall execute info? What do we need here? Or maybe we should just, for speed, just copy the create process from our injector. But we have it there. We have it. Yep. We also need our injector. Need this part, but we need to rename it. So since we are ourselves, we just want to start the same thing, and we want to add a command line l, run. It's complaining. And it wants it to be modifiable. That's and line. Oops, need to clone just line. 100 is equals. Yep. Okay. So now it will restart itself. So if we don't make child process debugging, we should first end up here and then not end up in the second call. Yep. Okay, that didn't work. Why? Because we passed the suspended flag. That was a small mistake. We want this to be null. Now it should work. And it just starts itself, and it just does something. So we have now changed our process such that we would need 2 levels of injection to reach our target. Now we can switch back to our DLL injector to be our main main target for injection. And now what we will need to do is we will need to hook another function. So we will make another function hook. Hook create process. Hook create process, and let's get this. Let's start with this. Now with hooking a create process, there are a few things to consider, namely that the create process function we are using here, what was it here, is not the only one. So there is also create process A, there is shell execute X, and so on. So what we might want to do is to make a hook such that we could catch all of those create process invocations no matter where they come from. But before we do this, let's quickly check whether this child process debugging thingy is really broken, because it would be much more convenient for a quick test if we would not need to manually attach to the debugger each time. So we are here, create. It's just broken for whatever reason. That's a pity. So if you use this without too many code injection thingies, then it works just fine. But apparently, it might be actually broken by this create suspended. I'll have to debug it. We'll just keep with manually attaching. So what we would want here is a function from the NTDLL. So let's get the address of the so we want the function. How is it called? Create process internal v. Or was it NT create process internal v? I don't remember. We will need to check whether we can find the function definition, and it might actually not be defined on the NTDLL. It might still be defined on the kernel 32 DLL. Okay, so we have create process X, and we have create process internal in the kernel 32 DLL. So okay, so there it is, and we will need to find the right definition for that. But let's first get our module kernel DLL. The thing is, on Windows XP there was just a kernel 32 DLL, but with Windows 7 a lot of its function were split out to kernel base DLL. So I think that we will need it from the kernel base. So we get what was it? Get module handle v kernel base 32 DLL. Or was just kernel base DLL? I think it was just kernel base DLL, and this needs to be an L. Let's quickly test whether that works in our DLL injector. So let's put a breakpoint here. And yep, we are getting a valid address. So the next thing we want is get pods address module, comma, create internal process W. We already have this somewhere in the clipboard. This always takes the ASCII version. So void asterisk p. We had the semantics to record it like this. Okay, let's see if that gives us the a valid address, and it does. So we can get the code to our injection DLL. This we already had, and then we can continue on our DLL injection. So what we will need, we can already get for here. We'll need our typedef, we'll need our trampoline, and we'll need our detour function. So typedef. Let me quickly see which I have. I had that typedef already somewhere, I think. The thing is, this changes also depending on the Windows version. Is this the right one? That should be the right one. think that's the right type for the Windows version we have here. If not, we will find it out early enough. And create process internal. And we wanted this to be null. Okay, so actually maybe the best approach would be to just copy this into our hook test and then just develop our hook there. So that's not the project, and once it's working as it should, then copy it back to our DLL. Okay, so we are here, we have the thing. We should add some create process just for testing, so let's go with copying this here for the test case. We don't want this, we don't want that, we don't really want the first one, we just want this. No. This we just write equals I forgot here. Okay, so we have our test case, we need a Strichpunkt. Yeah, well, so this our test case is our hook. Then we need our detour function, which we can copy from here. So this will be what was the right prefix? What WinAPI was here? I mean, this WinAPI is screw it. As long as we are in 64-bit, we don't need to care for the calling convention because all of Windows uses just the same one. The problem would only be present. Why is this not working? Type def. But it is. We just defined it. Okay, asterisk, it should be fine. It might, maybe one of those arguments are unknown. Let's just replace them with void asterisk and for process information. This can also be a void asterisk. It's still complaining. Why? Did not forget anything. Type def, type, name, arguments, handle is defined, oolong is defined, handle is defined. Let's see if the compiler gives us a better error message than the IntelliSense. Build errors, redefinition. Ah, shit. I was in process of turning this into a function and apparently did not like that. That's fine. Okay, so here for status we just call our okay, and this means all the arguments actually are available. And then we just need to pass all the arguments. Zack. Strichpunkt. And then we later we will modify this code to have the code injection, but now we just want the trampoline to work. So we are here. We have then we need void then my process x is equals this one. Process x internal. Okay, then what? Let's just copy the whole code starting from here, and then we'll just modify it as we go to work as it should. Okay, so hook the original function. This is what is that? Yeah. So we have this address and this thingy, so these are here. Zack. Create internal process there. Then we will need to see how this looks. Tab message box is also changed to this. Zack, Zack. Sorry, Zack. This one is with this. We don't need. We don't know if we need it, but let's assume we need it. We probably will need it. Yeah, that needs to be changed as well. Zack. Zack. Complaining about the. About this. Was it without? It was without V, I think. No. Sorry, here without V. Yep. Okay, that's inconsistency. Let's quickly fix that. V. V. Okay. So then we don't know what to do here yet. So we comment this out, and the detour code. We know what to do with the detour code. Then we need to unprotect this. Then we want to jump to wait. This, yes. Here it should be my. Wait, the copy and paste. Here it's wrong. Copying and pasting is so dangerous, but it's also so convenient. Okay. Okay. So for status, let's just do what? Let's put a return here. Put a breakpoint here. Then we will jump to this address and see. How the function looks at the beginning, so that we can craft. We have this rise. Okay, so that we can craft our trampoline. Okay, so this thingy. Oh, that's not good. We broke Visual Studio. Okay, I will need to restart Visual Studio because we broke somehow the disassembly view. That should not happen in normal use case. Zack. Okay, let's just rerun this. Debug window, disassembly. Okay, we go to this address. Zack. Oh, that might be a very nice trampoline. I think we have quite a few bytes without the need to change much. How many did we say we need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 12. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, that's more than enough. We just need. We can just take this part. Oops. Zack. So we have here our original code. How many is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's exactly as much as we need. That's nice. So we can write this plus 12. Yes, and we will not need the displacement thingy. We need, however, trampoline address. and 2 maybe. Yeah, okay. Let's start it here with a v 4340. We will need more because we need the jump code. So this is the 12. Let's just add another 12. The reason why this we should have added more to the trampoline in the other case as well, but the reason it works is that because the allocation here always allocates at least a whole page. No, sorry. We allocated here 32. It's enough. This one is just the target where to jump to. This is fine. This can stay as it is. This one is also enough room. Okay, so now let's continue with copying the bytes. So that will be a byte 56 57. Then we can copy the last 4 1 2 3 4 4 1 5 4 4 5 6 and shit, that's the wrong order. We always need to remember to swap the order when putting things into the hexadecimal representation in one piece. Here I remembered that this is fine, okay. And then we have our detour code. Then we have our original function where we write our detour. That should be it. The hook should be working. Let's try it out by putting a breakpoint here and see if we can successfully just start an instance of cmd.exe. Okay, run. Wait, we need to remove the test return. Okay, we ended up in the detour. This much was to be expected, and now if we continue, it started the cmd.exe. So this works, but we are running out of time. So just to quickly outline what we would want to do in the how high do I want to go? Wait, I could be too much. Wait, my process up to here. So to quickly outline what we would do in our injection DLL, we would have here the hook function, which we hook from here. So we know that this hook for this particular version of Windows works. So your mileage may vary. You probably this one I don't think it will change much because they're just saving a lot of registers to the stack. But this one here, the value might change, although probably not. Let me know if it. Sorry, what was it? Here. This value may change, but since we're using a displacement, it actually might work. So let me know if it's correct. If it's not, you just need to check your message box v and see which offset there should be in your version of the I guess the message box is in the user32 DLL. Okay, but to outline what would be needed to complete the inheritive hooking mechanism would be here to creation flags. To make creation flags is create suspended, then we need some more. So we want to see, so if this is false, then we just return. So if this, then return red. Or actually we could make it nicer. If red is true, then we do something, then return. And then here we should also have a for equals. So we want to know whether the flag was set before, and if it was set, we still, well, if it was set, then we are fine. If it was not set, so if is not create oops, if it's not create suspended, then resume thread. Process information. Punkt. Sorry. Yep. No. This one. So if the original caller didn't want the process to be suspended, then we resume it, else we don't. And here, this is the part for which we probably don't have time. What we want would be injected to. So basically, we now just copy everything from our injector, at least a reasonable portion of it. We need this. Maybe the time is enough. Create process we have. We don't need that. We don't care for disabling the parallel loading. Let's say for now, just want to inject DLL portion of the code. Wait for thread, but don't resume. Yep. So DLL loader path. Yes. The process information here we can grab from there. Okay, we use this a few times. 1, 2, 3. Yeah, and that should be it. We can try it out. We have 4 minutes left. So we switch to our DLL injector. Set as standard project. So this will start target app with the DLL injected. The target app will get the DLL injected, check its own command line, see that there is no run argument, then it will restart itself, at which point the new instance will be injected by the hook to create internal process V. And then when it goes again through the main, it will see, so let's put a breakpoint here, that the run was attached, and it will try to throw 2 message boxes, but our hook on the message boxes will suppress the first message box. That's the plan. Let's see if the plan comes together. Run. Okay, so this breakpoint we don't need. This breakpoint we need. Okay, now the one process is great. So debug. Attach to process. Target. Target app. Attach. So now when we resume, we should come out. Here, let's add another breakpoint just to be on the safe side. Let's add a breakpoint here, but we should come up here, and then later on we should come out here. So let's try it. Okay, that worked. We are in this hook. So this installs the hook, then we will come out target app here. Okay, this was fine, it's fine. We don't need a breakpoint then. We come out here, can step through the code, and when we then create process X, we should end up where we had the main at this breakpoint, and we do. You can see that in our call stack. Now we create it suspended, return is 1. We can see that there is, once it refreshed, another instance of target app to which we connect again. Yeah, we can only connect to one, the other one is grayed out because we are already connected. And then when we are in this thing, we would want to end up in our message box detour. So let's put a breakpoint there. Target app main. So if we run, yeah, we are in this debugger breakpoint, then we end up in main. Now we should step over it, which we do. And now if we run, the second injection failed. Why? Why? The second injection failed, and we need to debug that. Okay, so we are here, debug, attach to process, attach, continue. We are in the hook, that's fine. We are in this, that's also fine. And now we are here, so we create the thing. Try to get module test up. We create here our DLL path, which is correct. We write this to the memory. We get the address. Damn it. That should be, that's a mistake. H process. As I mentioned earlier, copy and paste is dangerous. I think it will now work fine. We just run the first thing, and as you see, the message box was suppressed, and the hacked app title is there, and we are perfectly on time. So, since we lost a lecture during December when I was sick, I will have one more lecture next week. If you want to come, please come. If you are already in exam mode, then you are free not to come. During the next lecture, I will also demonstrate some of these nice things that you can do with C++, which in very exotic edge cases might be highly useful, but usually probably might not. Yeah. Any questions? If there are no questions, then we are done for today, and we might see each other next week, or not. Also, maybe one question to the group. Would you be interested in like a part 3 of C++, low-level C++, or not? We would see. I would have to think about something. It's yes. Well, if we have enough interested people, we could make like part 1 and 3 run in parallel. Yeah. I don't know. We have at least the potential for candidates. Yes. Okay. Mhm. Okay. Okay. So. Okay. Um. Mhm. 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 Um. Okay. Any more yeah? Yes, that is one thing we could do. That we come up with subjects with topics which the students want to cover, and then we see where we go from there. Mhm. Mhm. Okay. Yeah. So would there be an interest in a seminar of this sort? Okay. So we have 2 candidates already. I don't know if there's even possible to organize. I was just wanted to know whether there is interest, and if there would be overwhelming interest, I could then just ask our administrative personnel if that's even possible. Mm-hmm. Mm-hmm. Okay. Mm-hmm. Okay. Okay. Good. Then I think about it. Let's see where it goes. Good. Are there any other questions from you about the final project or something? Or can we stop for today? Okay, then whoever wants to come next week is welcome, but it's not mandatory since since the semester technically ends this week, I think. So maybe see you next time or see you somewhere else. Yes. See you. Bye bye. Już. A pomyślałem sobie, że jakby było interesentów, to mógłbym powiedzieć, że tyle studentów chce więcej wykładów, a za wykłady powyżej tych 8 godzin musiałaby mi uczelnia płacić. Ale miałem tylko 3 studentów, plus tego to